Weight shift control 6-3 flight maneuvers. When an aircraft initiates a climb, its flight path changes from level flight to an inclined plane. Weight, which was acting perpendicular to the flight path, now acts in a rearward direction, leading to an increase in total drag. To sustain a climb, thrust must be increased to offset the elevated drag, and climb is ultimately limited by the available thrust. Climb conditions include normal climb, best rate of climb, Vy, and best angle of climb, Vx. These should be performed with knowledge of power settings and pitch attitudes recommended by the aircraft manufacturer. Normal climb is executed at the recommended airspeed, usually Vy, which is the airspeed maximizing altitude gain in a given time. Vy, made at full allowable power, is the most efficient speed due to its optimal lift-to-drag ratio. Best Vx, the airspeed producing the most altitude gain in a given horizontal distance, is used for steep climb paths and obstacle clearance. Climbing flight demands more power than level flight, and power adjustments are crucial as the engine experiences reduced power with altitude gain. During climbs, a constant heading is maintained, and in climbing turns, attention is given to outside references and traffic scanning. Climbing turns are advantageous for visibility and are recommended when ascending to a practice area. Shallow turns are preferred to maintain an efficient rate of climb, and factors affecting level turns also apply to climbing turns. Common errors in climbs and climbing turns include excessive bank angles hindering efficient climbs, improper airspeeds, attempting to exceed the aircraft's climb capability, and difficulty in maintaining constant pitch and bank attitudes during climbing turns. The use of inside flight deck instruments for establishing climb pitch attitude is discouraged to prevent chasing airspeed. Let's discuss descents and descending turns. When an aircraft enters a descent, it changes its flight path from level to an inclined plane. There are various ways pilots manage descents. The partial power descent, often termed cruise or en route descent, involves descending with partial power. Pilots maintain the airspeed and power setting recommended by the aircraft manufacturer for a prolonged descent, targeting a descent rate of around 400 to 500 feet per minute. In a steep approach, used when rapid descent is needed, the throttle is set to idle, and the airspeed is increased to allow for a steep descent. Pulling in the control bar helps achieve a steeper angle. Another method is a descent at minimum safe airspeed, creating a nose-high descent. This is used for specific situations, such as clearing obstacles close to the ground, but caution is advised due to the risk of stalling. Finally, there's the glide, a basic maneuver where the aircraft descends in a controlled manner with little or no engine power, utilizing gravity to follow an inclined path. The glide ratio is the distance traveled forward relative to the altitude lost. Finding the best glide speed is crucial, as it corresponds to the airspeed at which you cover the greatest forward distance for a given loss of altitude in still air, ensuring the best lift-to-drag ratio. Attempting to stretch a glide by pulling up and slowing down below the recommended best glide speed is strongly discouraged, as it can disrupt the descent and lead to an inadvertent stall. Instead, pilots should adhere to the recommended speeds. After closing the throttle, adjusting the pitch attitude is necessary to find the best glide speed. Once achieved, the aircraft may need to be retrimmed if necessary, allowing the pilot to maintain that attitude without constantly holding pressure on the control bar. Understanding the interplay of pitch, power, and finding the best glide speed is crucial for effective descents. With practice, these principles become second nature. No discussion of climbs and descents would be complete without touching on the question of what controls altitude and what controls airspeed. The pilot must understand the effects of both power and pitch control, working together, during different conditions of flight. As a general rule, power is used to determine vertical speed and pitch control is used to determine speed. However, there are many variations and combinations to this general statement. Decreasing pitch and diving do provide a quicker descent but is not typically used as a flight technique for long descents. Changes in pitch through moving the control bar forward and backward are used for maintaining level flight in rising and falling air, and pulling back on the control bar is used for a steep approach technique to lose altitude. However, these techniques are used only for short durations and not the primary altitude control for the weight shift control. The throttle is the main control used for determining vertical speed. At normal pitch attitudes recommended by the manufacturer and a constant airspeed, the amount of power used determines whether the aircraft climbs, descends, or remains level at that attitude. Now, let's delve into the steep turn performance maneuver. The objective of this maneuver is to develop the smoothness, coordination, orientation, division of attention, and control techniques necessary for the execution of maximum performance turns when the aircraft is near its limits. The steep turn maneuver consists of a level turn in either direction using a bank angle between 45 degrees to 60 degrees. This causes an overbanking tendency during which maximum turning performance is attained and relatively high load factors are imposed. Because of the high load factors imposed, these turns should be performed at an airspeed that does not exceed the aircraft's design maneuvering speed, VA. The principles of an ordinary steep turn apply, but as a practice maneuver, the steep turns should be continued until 360 degrees or 720 degrees of turn have been completed. An aircraft's maximum turning performance is its fastest rate of turn and its shortest radius of turn, which change with both airspeed and angle of bank. Each aircraft's turning performance is limited by the amount of power its engine is developing, its limit load factor, structural strength, and its aerodynamic characteristics. Do not exceed the maximum bank angle limitation in the PO. For example, a maximum 60 degrees bank angle is a limit used by many manufacturers. The pilot should realize the tremendous additional load that is imposed on an aircraft as the bank is increased beyond 45 degrees. During a coordinated turn with a 60 degrees bank, a load factor of approximately 2 gigaseconds is placed on the aircraft's structure. Regardless of the airspeed or the type of aircraft involved, a given angle of bank in a turn during which altitude is maintained always produces the same load factor. Pilots must be aware that an additional load factor increases the stalling speed at a significant rate. Stalling speed increases with the square root of the load factor. For example, a light aircraft that stalls at 40 knots in level flight stalls at nearly 57 knots in a 60 degrees bank. The pilot's understanding and observance of this fact is an indispensable safety precaution for the performance of all maneuvers requiring turns. Before starting the steep turn, the pilot should ensure that the area is clear of other air traffic since the rate of turn is quite rapid. After establishing the manufacturer's recommended entry speed or the design maneuvering speed, the aircraft should be smoothly rolled into a selected bank angle between 45 degrees to 60 degrees and the throttle increased to maintain level flight. Always perfect the steep turn at 45 degrees and slowly work up to higher bank angles. As the turn is being established, control bar forward pressure should be smoothly increased to increase the angle of attack. This provides the additional wing lift required to compensate for the increasing load factor. After the selected bank angle has been reached, the pilot finds that considerable force is required on the control bar, and increased throttle is required to hold the aircraft in level flight, to maintain altitude. Because of this increase in the force applied to the control bar, the load factor increases. In a steep turn, you've got to remember that pushing that control bar forward increases the angle of attack, and that brings up the drag. So, you'll need to add power to keep that entry altitude and airspeed in check. But here's the thing. When you're turning, don't just stare at one spot. You need to be aware of where that forward tube is in relation to the horizon to keep your altitude and orientation in check. And, of course, keep an eye out for other planes, especially in the direction of the turn, while glancing at your instruments to ensure you're on target with airspeed and altitude. Now, if your altitude starts playing games, you might need to make some power adjustments to keep things steady, considering that constant bank angle and speed. And remember, when you're changing that bank angle, do it smoothly with a coordinated mix of pitch and throttle control. Timing is key when rolling out from the turn. You want those wings level exactly when you're back on the heading where you started. As you recover, ease off the forward bar pressure and cut the power as needed to hold that altitude and airspeed. But, like any maneuver, there are common slip-ups to watch out for. Make sure you've cleared the area adequately. Too much pitch change during entry or recovery is a no-no. And don't jump the gun when you're trying to start the recovery. You've got to nail that precision, stopping the turn dead on that precise heading. Managing power is crucial. You don't want to be gaining or losing altitude unexpectedly. Keep a close eye on your airspeed, it's easy to get that wrong. And, of course, coordination is everything. Roll, pitch, and power all need to work together. Hold that bank angle steady, and don't forget to scan for other traffic before and during the whole maneuver.